Thank you so much. I want to welcome you to another multivariate statistics class. Of course, wait a minute. Give me- no. Okay. Okay, so I want to welcome you to another multivariate statistics class. Let me say this. We're getting closer to the final. I want to believe attendance of classes now very, very crucial because what is going to be in the final is highly mathematical. So I'm actually going to release a final practice question very early, and that will be released on Friday. So watch out for that. It's going to be highly mathematical because I want to make sure um, ahead of time you know what is coming. You know the areas that we actually are going to concentrate on. I want to welcome you to canonical correlation analysis. But before I get started, I think I need to make a distinction between, uh, principal component analysis, factor analysis, and what we want to start today that we call canonical correlation. So let's start from this. I'm going to use, the athletic data example that we used before, okay, so that you'll be able to distinguish, okay, between the three. Number one, let's start with the principal component analysis. I have so many variables, and these are athletic variables, particularly this is the decathlon, where athletes participated in more than one event. So what the principal components analysis we do is to summarize the data, summarize in a way that it's actually, you could say, maybe for instance, you derive fewer dimension to represent the numbers of events, or the first principal component may actually be, maybe let me just write PC1 may actually represent maybe the overall athletic ability, overall, okay, athletic ability. What is the meaning of overall athletic performance? Is just like an athlete actually perform good in all the events. That is what it means. Okay, so the PC1 may be talking about that. Why PC2 may be talking about differentiating some events that involve strength, some event that involves strength, okay, from events that involve speed. This I need you to pay attention. I want you to see the difference. Now, right now, I'm working on the PCA. Okay. Now, maybe I've arrived at PCA1 and PCA2. The PCA1 may be talking about overall athletic performance, while PC2 may actually enable us to distinguish speed from strength. Of course, we're talking about speed event, talk about the 100 meter, the 400 meter, the hurdle. Okay, I want to talk about strength. There are some events that you need to have the strength ability, maybe like the discus, the shot put, or the javelin, and so on like that. Now, that is the job of a PCA. But now let me not tell you this. PCA does not actually do grouping, okay? It doesn't do grouping. It only summarizes, okay? Now, the performance. But if I go to factor analysis now on the same data, okay, the factor analysis actually want to identify the underlying latent ability. You know, athletes don't just perform randomly. They perform because they have hidden ability. So the factor analysis want to uncover the hidden ability. Okay, now maybe for maybe factor one, we have factor one, we got factor two, we got factor three, and maybe factor one may actually be talking about speed. Okay, speed ability. Okay, and maybe factor two, maybe talking about strength. Okay, maybe talking about strength. Okay, and maybe factor three, maybe talking about endurance. Endurance. Now, when you take a look at initially, these abilities, they were not observed. They were actually underlying ability athletes have. We actually figure them out, we extract them, we'll cover them through factor analysis. Now, you're actually going to see all the events that we have will be grouped. We're going to have some events that are for speed. Maybe you want to talk about 100 meter, we want to talk about 400 meter. Then event that requires strength, okay, maybe the discus or maybe all the throwing events. Okay, the event that require endurance, like a long distance event, like maybe 1,500 meter, because I remember when in my former district, Plymouth, they organized marathon and everybody around, and my daughters actually came before I arrived, so I I can't cope with endurance events. It's not easy for me, but I can do sprints. So I think I'll give kudos to those who do endurance event. Now the factor analysis is about grouping. Okay, it's not going to summarize, just going to group events into that. But let's take a look at what we want to do today. What does canonical correlation does? The canonical correlation at the beginning, we're actually going to have two sets of events. Okay, if I want to use the catalog, okay, I'm just giving you an idea before we start. Okay, before we start, so maybe X may be events that are classified as feed events, and Y the event on track. Please pay attention. Okay, to talk about canonical correlation analysis, we actually need two sets of events where some events will be classified under feed, some event will be classified under track. And we now want to see if relationship exists between the feed events and the track event. That is just a difference. So this canonical correlation talk about, relationships, investigating relationship between two sets of events. Under feed event, don't forget, we have so many. We're going to have X1, X2, and so on like that, right? On the track event, we're going to have Y1, Y2, and so on like that. But why is it that I cannot do that without canonical? Why can't I just relate a particular feed event with a particular track event? There's going to be a lot, and that would be so messy, okay, to do. And that's why we need a canonical correlation to do that. Now you can see the difference between the principal component analysis, the factor analysis, and the canonical correlation. Okay, let me say this. Okay, all of this will be on the final exam. So I'm trying to let you know You're going to be on the final exam. The final exam is not going to be cumulative. Okay, all of these will be on the final. Okay, now let's. Okay, so I need someone to confirm if you're hearing me. Those of you that are online.
Yes.
Okay, so I'm introducing you to canonical correlation analysis, and I just differentiated between what is the connection between the principal component analysis, factor analysis, and the canonical correlation. I'm going to say that one more time. When you talk about principal component analysis, that actually handles summarization. Okay, so using the Decathlon athletic data that we've been using, the principal component analysis, okay, we actually enable us to use a fewer dimensions that we artificially fabricated. If we identify two principal components, the PC1 may actually represent the overall athletic performance for a particular athlete, while the PC2 may separate, maybe differentiate between the speed event, and the one that involve strength. But when you talk about factor analysis is about grouping. Okay, you want to identify, we believe an athlete don't just perform randomly. An athlete has a particular ability that is hidden that we need to uncover, and that we can only uncover that through analysis of factor model. And of course, if at the end of the day you're able to have three factors, the first factor may actually represent the speed, the second factor may represent the strength, and the third factor may represent endurance. So which means all the events that you have will be categorized. Okay, so factor analysis is about grouping, but you group the original features based on the underlying factors you have identified. But for canonical correlation, okay, we want to look into what is the how set of events, set of input events, okay, relate to set of another event. That's what canonical actually talk about. And why is it that we cannot actually look into this relationship directly? Why not between a particular X and a particular Y? Why not looking at the relationship between long jump that is done on the field and the 100-meter that is done on the track? Why can't I look into that? I'm going to look into a lot situation where I got a lot of events in the field event, and I got a lot of event in the track event. So the common sense way of doing that is actually to go canonical, because the canonical we actually make what is expected to be messy to be very clean. Because of that, I want to welcome you to canonical correlation analysis. Let me tell you this. What I always pay attention to in class is actually when I understand the intention. Because what I'm going to be showcasing now are going to be equations, model. But the moment you understand what our intention is, everything is going to be easy. Okay, so this is I'm going to talk about all of that. We're going to talk about the population, the sample estimate, last samples, the Decathlon example. So let's get started. Now, I think I just explained this to you. Now, please pay attention. We're going to have two sets of variables. Look at that. First one, the second one. Two sets of variables. Okay? In principal component analysis and in factor analysis, we only have one set of variable. This is the first time that we're going to consider two sets of variable. Okay? Correlation actually require two variables. You get what I mean? That's why we need two set of variables. Now, when I have two set of variables, okay, if this is the x variable, there's going to be a mean vector for that. If this is y variable, there's going to be a mean vector for y. Then, uh, for x variable, I'm actually going to have the covariance matrix for x. For y variable, I'm also going to have the covariance matrix for y. Can you see that? Okay. Now, I'm actually going to say that, okay, uh, if I want to consider a particular z, which is actually combining x and y, then I'm actually going to see z to follow a distribution with a mean vector and the variance covariance. Now, if I have this guy, I'm going to have that as the mean. Where if you take a look at what is happening here, set of this one, we have this as the mean. Okay, set of y, we have this guy as the mean. If I want to write, if you take a look at this guy, can be defined as this. Because you know why? I'm actually going to have the covariance matrix for x, the covariance matrix for y, then I'm also going to have the covariance matrix that combine x and y. Is there any question here? Okay, so if you take a look at all of this now, this become a general covariance. A general covariance. Okay, inside the general covariance, we also have some covariances. If you look at the diagonal, if you look at the diagonal here, the covariance S, the covariance Y. The covariance S is a matrix on its own. The covariance Y is also a matrix on its own. The off diagonal, this guy, is also a matrix on its own. So what I have here is actually a general combined matrix. Okay, now, and if you really want to understand this guy that you're talking about, the covariance between x and y. If I want to get a correlation between x and y, I need to first get the covariance between x and y. If the covariance between x and y does not exist, the correlation is not going to exist. We all know the connection. Okay, but let me tell you this. Getting the covariance of a set of x and y may be messy. I'm going to say that again. Getting the covariance of the set of variable x and y, because we have so many values under x. We have so many variables under x. We have so many variables under y. So getting the covariance of the original variables would be messy. And that is why we actually we believe that the moment we get a canonical correlation, we can actually recover that. We can recover the original covariance. So what are we going to do? I need you to pay attention. What we actually going to do now moving forward, okay, we actually have to do with principal components. We're going to use the idea of a principal component. Take a look at this guy now. This is going to be linear. I'm actually going to have a u. And that very u now, okay, is a new variable. And it's going to give us a linear combination of the original x variables. We're also going to have a v, which is also going to give us a linear combination of y variables. Does that make sense? So which means it's like I'm actually doing principal component, but instead of doing principal component on one set, I'm doing it on two sets. Does that make sense? If you take a look at what I got. Okay, now we have defined, we're going to have new variables, like I said. Now, and I need you to pay attention. This is a canonical variate. Now, u and v are called canonical variates. Canonical variates are actually derived, they are linear combination of the original features in S, original features in Y. So they're going to be they're going to be variates. In fact, they're going to be random variable. If they are random variable, we can actually look into the variance of the canonical variates. We can get the variance of U, we can get the variance of V, and at the same time, we can get the covariance of U and V. Is that not interesting? So the formula to get this is actually given here. Take a look at this. If I want to get the variance of U, don't forget, U is a what? U is a linear combination of X, right? The other time, using the Cartesian data, we are call X field event, right? Field event like shot put or javelin or discus, those are field event, okay? And the Y, I call that track event, 100 meter, 400 meter, and so on like that, okay? Now, U is a canonical variate that I derive using the linear combination of the field event, and the V is actually the canonical variate that actually are derived using the linear combination of the track event. And of course, because they are variable, I can find this is the variance. If I want to find the variance of U, if I want to find the variance of V, if I also want to find their covariance. But you know what? If you take a look at this, if I want to find the variance of U, I only need the linear, the A, they are very a constant A, that is more or less the same thing as the eigenvector, the loadings that we talk about under principal component analysis. And this guy here is the covariance for X, for set of X. Okay, just wanted to take a look. The same thing with that. If you come into the covariance now, okay, look at that. You're actually using the loading, okay, for U variate, loading for V variate, and you're actually going to use the covariance matrix connecting X and Y. Look at that. The covariance matrix connecting X and Y. Okay, just wanted to see that. I'm moving now. Now, do you know that the moment I got, let me tell you this. Uh, some of you may be wondering, okay, why do I need, why do I need, why do I need all of this? Without all of that, I may not be able to get a correlation. Okay. Or, if you take a look at here, okay, this guy is actually the one here. This guy is actually the one here. This guy is actually the one here. So without you having the covariance for the canonical variate, without you having the variance of U, the variance of V, there's no way you'll be able to get the correlation between them. Does that make sense? Okay. Now, using all of that here, okay, substituting that will lead us into that formula. Is there any question whether in person or online? Any question? Is there any question? Now, assumption here is that they are subject U1 and V1 as they have a unit variance, which is 1. Okay, now I'm actually moving. I'm moving. Now, let me tell you this. Where there will be so many canonical covariates that we're actually going to derive. Okay, on for U, we're going to have U1, U2, U3, and so on like that. We're going to have V1, V2. But you know what? The first one, U1, V1, okay, we actually have the maximum variance. Now, let me tell you this. You remember under the principal component analysis, the first principal component analysis, we have the largest variance, right? Okay, now, but you know what here? If you take a look at this, I said the remaining canonical covariate maximize the above subject to having univariance and being uncorrelated. We actually have assumption. Any two different canonical covariate, they actually need to be uncorrelated. Like for instance, if I take a U1, UK, and a VK, okay, they have to be uncorrelated. And you're gonna see why they have to be uncorrelated. But you know what? Let me move. Okay, please pay attention. This is where it's getting complicated. We're gonna make use of a formula. Okay. Now, you know, take a look at this. Um, if I have, let's say, uh, under X features, okay, if I have X1, X2, please pay attention, X2, until I get to XP. Okay, when I'm deriving canonical variate for that, I'm not going to use, I'm not going to have U1 not to UP. I'm only going to take fewer one. Don't forget, the same with the principal component analysis. So, you're going to have U1, U2. The possibility is having that U up to what? UP for X1 up to XP. But we are only going to take fewer ones without we are approximating. Does that make sense? The same thing with Y. If I have Y1, right? Y2 until we get to YQ. Why do I say YQ? Because the number of element, the variable in S may not be the same as the numbers of variables in Y. But here, the canonical variate that we're going to derive for that will be V1, V2, until you get to VQ. But you know what I'm trying to say, okay? For this one, we're not going to use U1 or to UP. For this one, we're not going to use V1 or to VQ. We're only going to take few ones. The same thing that we did in the principal component analysis. But if I want to, it's just like the same way that I only talk about, okay, I want to talk about a particular principal component K. But you know what? Here, I'm considering a particular canonical variate for U and V is this guy here. Please pay attention. Okay, this is what we call the Kate pair of canonical variate, which means I'm focusing on a particular one. It may be U1 V1, U2 V2, U3 V3. Does that make sense? So that's exactly what I'm trying to say. Now, if I want to get a particular one, please pay attention. The question now is, what is this guy? Okay, how am I going to get that guy here? I already know my X. My X is my data. This is easy to get. That is the inverse. When you take they have inverse of the covariance matrix for S. But the question is, how am I going to get this? This guy, please pay attention. This guy is the eigenvector of this guy. I have to first get all these matrices, okay, into one, multiply all of them into one. Then I will need to get the eigenvector of that to be able to have access to UK. If I want to get access to this one, I also need the same here, eigenvector of this one. Okay? So eigenvector of that, eigenvector of that. Does that make sense? But if you now, generally speaking, this one is just this. This one It's just that. It's more or less like this guy is a linear combination of that one and X, and this guy is a linear combination of this guy and Y. So the idea of eigenvectors is going to be applied here. But eigenvector of what? You need to get this. Okay? You need to get that. Okay? We now find the eigenvector. But you know what? The good news, this can be done in R. That is good news. I'm moving now. Now, after getting this and this, I can't get this and this without getting this and that, which is why this is very essential. So if I have my UK and my VK, I can now find a correlation. Can you see that? That's going to be like a Kate canonical correlation. Maybe correlation between U1 and V1, or correlation between U2 and V2, correlation between U3 and V3, and so on like that. That's what it means. But you know what? Another thing, if you take a look at this guy now, okay, when I square this guy, when I square this, do you know that that guy is the eigenvalue of this guy? Okay? If I want to, for instance, if I want to get R squared, you know, when I get R squared, it's very easy to get R. I just find the square root, right? I can get R squared directly, finding the eigenvalue of that. If I find the eigenvalue of that and I get Roy's square K, when I find the square root of that, that will give me my canonical or, correlation. So that's another way you can get it out. Okay, now just giving you some formula here. Okay, what do you want to do here? Is there a relationship between original variable and the canonical variables? The canonical variables are the one that you derive using a linear combination of the original. The question now is, we want to talk about, is there a relationship? What do we expect? We expect relationship, right, between them. Now, the canonical variable that we derive from X is that. The one that we derive from Y is V. Okay. And don't forget, here, A1 to AP, B1 to BQ, and we have to impose this. If P is less or equal to Q, we are interested in the first P canonical vary from Y. So I wanted to see that condition. What is P? P is probably the number of variables in X, is what we call P. If it is less or equal to the numbers of variables in Y, okay, then we are interested in the first P canonical variate from Y. Whenever that happens, we're interested in that. Now, I'm moving now. Let's take a look at that. You know that? What is it? We want to measure how canonical variate that you derive from set of X, how it is related with the original X. Do you see that? You see what we're doing here? We want to investigate we want to see how do they vary together or not. U is a canonical variate derived from the linear combination of X. Okay, and X. But do you know that U itself, please pay attention, U itself is this, right? That is U, right? Now, in the end, if I take a look at this, this is just going to be that. It's just going to be the transpose of the constant, okay, the linear combination multiplied by the covariance of X. If I want to look into the covariance between U and Y, okay, because of the fact that U is AX, then Y is involved, then the covariance matrix that connect X and Y would be involved. That's why you see that. If I want to look at this, the covariance between the covariate, the V is a canonical variate derived from Y. That's why you see this, right? You want to look into that relationship between with S, then there's going to be this. If you are only looking into the canonical, looking into the how V, which is a canonical variate derived from Y, how it relates to the original Y, okay, then this is the formula. So take a look at that. So we can actually investigate that. Okay, now the moment we know that of this ones here, focus on the covariances. Then we can also talk about the one that focus on correlation. Okay, covariance is different from correlation. So let's take a look at the one. Oh my God, take a look at what I have here now. This is giving you formula. Okay, correlation, 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 correlation. So you are looking into correlation between the canonical variate derived, okay, and the original feature X and Y. So those are the formula, okay. And of course, if you take a look at this guy, let's take a look at that, all of that, okay. They actually represent the diagonal of this. See, there's a difference between this guy, and this guy. Can you see that? Can you see something on that? That guy is just the diagonal element that of the covariance matrix X. If I have a covariance matrix X, okay, the diagonal is that guy. That's what he's talking about. So please pay attention to that. Okay, now canonical variates are summarizing variability. Okay, now the linear transformation that and defined to the idea here is, can we have a way to maximize correlation between the canonical variables? That is the essence of canonical correlation. How can we maximize, okay, relationship or the correlation between the canonical variables? But let me tell you this, it's different from this. Not the same as maximizing the explained variance. You know, in the principal component analysis, the idea is to maximize, explaining the variance. It's about variance maximization. That's principal component. But this guy is not maximizing that, but it's only maximizing the relationship, the correlation. Maximizing relationship is different from maximizing the explained variance. So just to let you know, not the same as maximizing the explained variance in that. Okay, now everything that we've been talking about population. Okay, but we don't have access to the whole population when you are doing research. So we actually want to look into this now when we're focusing on the sample. Let's pay attention. Focusing on the sample now, you can say this is we actually have an assumption. Assumption is that I have two set of variables. Set of variable in S, set of variable in Y. They are both jointly normally distributed. They follow normal distribution with the mean vector, mu, and the covariance. Take a look at that. We're working on sample now. For sample situation now. Okay? For sample situation now. Okay, so where your mu, you're going to have a mu for the set of S, mean for the set of Y. You're going to have a general covariance. Like I said, this is the covariance for X, a set of X, covariance for set of Y, the covariance for X and Y. Okay. And you know what? Because this guy is a population mean vector. But this is is a sample mean vector. This is a population covariance. This is a sample covariance. Please look at the difference between the two. Okay? Or these ones are for population. Okay? When you have all the data, when you are working with the whole population. We don't work with the whole population in research. We normally take a sample. So the one that we're going to be focusing on is actually going to be this guy, where samples are involved. Okay, where you can get the mean X bar and Y bar from your data. Okay, look at the formula here. Oh, I want to get, well, what is the X bar? Oh, find the mean. Okay, but there's going to be several means. Don't forget, maybe X represent speed event. What is the mean score? Okay, mean score for long jump, the mean score for pole vault, the mean for high jump, the mean for each variable in the field event. You're going to get that. Okay. Then the mean for each variable in the track event. You're going to get that. The variance. This is the variance for the track. I mean, for the field event. The variance for the track. Then the covariance. So this is explaining how you get all of these. Okay. I'm moving on. And of course, this is, the other time we did not put a cap. You know why we put in this a cap? A cap. That means estimate because we're working with sample. Whenever we're working with sample, we put a cap. We're estimating. That's what it means. Okay. This is what we're looking for. Okay. That's what we're looking for, right? Okay. Now, these are the estimates of the variance for U, for V, and for the UV. At the moment I have that, then I'm going to have the estimate for the correlation. Look at that. I'm having the estimate for the correlation. I remember the other time, this guy, what we put here the other time was this. Whenever you see that sign, that's for correlation. This guy is for this guy is for population. Why this guy is for sample. Okay? So that's what we're redefining now. Everything that we've done before, we're just reproducing that back in a sample form. Okay, in a sample form, all of that in a sample form. We've already done this in population form. Now in a sample form, we're having that in a sample form. Okay, now up to here, this is a correlation in a sample form. Correlation. Correlation, you can see here, correlation between what? Between this guy that you estimate and your X. Correlation between this guy that you estimate. That's why they're having a cap. Having a cap means I'm getting there from sample. I'm working with sample. Okay. I'm actually moving now. What do I want to do here? Covariance matrix implied by CCA for A. I want to explain something here. You know, if I actually have a canonical correlation, is there a way I can recover the original covariance for original variables? Why is it that I don't want to get that in the first place? Why do I go for canonical? Because if I go for that in the first place, it's going to be messy. And we believe that canonical will produce a very cleaner picture of reality. Now, I wanted to take a look at this. You know, what is this guy talking about? What is the covariance of estimate of canonical variate derived from the linear combination of original feature X? Okay. Now, this is the same thing because we're talking about focusing on S. The covariance that you're going to see in the middle will be sample covariance for X. Don't forget this guy, we actually got that guy from a linear combination of AS, right? Okay, so now what we're trying to tell the world that when I we expect this guy to give us identity because we're told the other time that if I'm focusing on the canonical variate itself, it has a unit variance. Unit variance means 11111. But here, because we're going to say identity. You know why identity? Because in the diagonal of identity, what do you see? 11111. Does that make sense? Okay, that is what this guy is trying to talk about. But you know what? Mhm. I'm moving towards something now. Let's play a mathematical game. I'm still going to use this material on Wednesday, but let's play a mathematical game. We know that this guy gave us identity, which is this. You know what I want to do? Please pay attention. If I multiply both sides, if I multiply by inverse of a transpose A and the inverse of A, look at that. You know what I want to do? I'm talking about this guy. I pre-multiply by this and post-multiply by this. This guy is the one in the middle here. Just pay attention. You know what I did? Pre-multiply means what comes first. Pre-multiply by inverse of the transpose of the estimated A and post-multiply by the inverse of the estimated A. Okay. You know when I do that? Because the one in the middle is an identity as given. I'm only going to have here, this is just going to be identity, right? If I use this times identity times that, I'm still going to have that. Identity will disappear, right? Please pay attention. Now, if you look at what I have here, this guy in scalar form is the same thing as this. You know what I've done? I've been able to recover sample covariance for original feature from the canonical. That is what I've done here, which is trying to tell me that the original sample covariance, I can actually recover that when I have the canonical. Okay, so the original covariance for S that will recover, from the canonical is a very fine structure. It's different from the one that you did not actually get through that. And because of that, I'm actually so what I'm actually telling the world is that I'm reconstructing, I'm trying to recover the original covariance of matrix X from the canonical structure. And in doing that, what I've been able to do is that actually this is actually built from the combination of that. So this can be trusted. Okay, this can be so. The bottom line here is if I have a canonical, okay, from the covariance of a canonical variate, I can recover because there's S is part of this because this guy is actually a linear combination of S. And that is the reason why I can recover the covariance that has to do with S. Okay? That is what this guy is actually talking about. Then I can do the same thing for V. Look at that. The one for V. Don't forget, this guy is a linear combination of Y, right? So doing what I did the other time, I can also recover. I can recover the covariance for Y. Okay? Now, take a look at this. This is a covariance for Y. Okay? So, which means I can recover that. I can recover the original covariance for X from the canonical variate, okay, from the covariance. Okay, this is what happened. I can recover original covariance for X from the covariance of the canonical variate U. Don't forget, U is a linear combination of S. I can also recover the original covariance for Y from the covariance of canonical variate V. Okay, which is what I'm doing here. Can you see that? I'm going to stop here today. And we're going to continue from here on Wednesday. Okay, that's all I got. Make sure you all stay safe and have a lovely day. Bye for now, everyone.